So Kamil has been involved in biophysical modeling of the bold fMRI signal for many years, an expert in understanding the mechanisms behind bold, as well as laminar fMRI technologies, ultra-high field technologies. We heard about his anatomical imaging approaches. So I think a cognitive neuroscience with a strong MR physics background, and we're very happy to have you here today, Kamil. So thanks so much. Looking forward to your presentation.
Yeah, thanks for organizing this course. It's quite amazing. I learned a lot, and you're all quite lucky because I've been in the field, in laminar fMRI field, around like 10 years, and the field has undergone so much development. I think it's now a mature field, and a lot of interesting cognitive neuroscience will come out in the next few years. So initially, I will, so this is an overview of my talk. I will initially talk about standard resolution modeling, because this will sort of set the stage for what we need to take into account when we go to higher resolution fMRI. And then I will talk about the ascending vein problem. And then at the end, I will talk about how we go from neuron to the voxel level. Essentially, these are sort of three different papers we have published in the last 6-7 years. Okay, modeling the standard fMRI signal. Just as a reminder, we have neuroactivity, and we have heard a very nice talk by Josine about that neuroactivity itself is a very complex notion. It changes oxygen metabolism. Oxygen metabolism increases the amount of deoxygenated hemoglobin, and deoxygenated hemoglobin is paramagnetic, which decreases the bold signal. And this was actually initially expected when fMRI was invented, that with neuroactivity, the bold signal should go down. Ogawa sort of wrote in his paper 1990 that perhaps neuroactivity, you can detect neuroactivity and the bold signal should go down. As you know, bold signal goes up, but this already is something puzzling effect to think about. And the reason why the bold signal goes up is we have also an increase in blood flow called neurovascular coupling. This decreases the amount of deoxygenated hemoglobin. And this increase in blood flow is approximately 2 to 4 times increase of oxygen metabolism, even though this is still debated. And therefore, because deoxyhemoglobin goes down and deoxyhemoglobin is paramagnetic, the bold signal goes up. Finally, we have the effect of blood volume. Blood volume increases oxygenated hemoglobin and deoxygenated hemoglobin because just the blood, there's more blood. And this leads to a decrease in, increase in deoxygenated hemoglobin. However, the effect of blood flow is stronger than the effect of oxygen metabolism blood volume, and therefore the total amount of deoxygenated hemoglobin goes down, and we have a bold signal increase. And this is sort of described by the so-called balloon model. There's also a direct effect of blood volume on the bold signal if the intravascular and extravascular relaxation rates are different, which means the apparent proton density changes when the blood volume increases. And this has been a short letter from me. This might be an explanation for why some people observe the so-called initial dip, but I will not talk into much into that. So if you want to model this entire chain from neuroactivity to the bold signal, we have to look at the picture like this. This was done by my former postdoc. We have sort of neuroactivity, whatever this is. We have energy consumption, oxygen metabolism, neuroresponse. We simplify it by 1 or 2 different functions. Then second is the neurovascular coupling. Third is the hemodynamics. And the fourth would be the translation from deoxygenated hemoglobin to bold response. And we have developed a model which we embedded in the dynamic causal modeling framework and called it physiological dynamic causal model because it was inspired by physiological knowledge at that time. So the neural level we model as excitation inhibition. So we have 2 different populations, excitatory neurons, inhibitory neurons, they interact with each other. And 2 brain areas interact with each other on the mostly excitatory neural level. We have neurovascular coupling, which we think is a feed-forward mechanism, which means when neurons are active, they just release substances and blood flow increases. regardless whether the blood flow was already sufficient or not. It's a feed-forward mechanism because some models like the DCM in SPM has a feedback, and this we could show that actually this is not physiologically realistic. Then we have the hemodynamics and so on, and this has been published in 2015, and we had few follow-up papers. One interesting finding from this is when we analyze the same data for connectivity, this sort of links to the previous talk. When we analyze effective connectivity, you get different effective connectivity profiles when you use different hemodynamic models. So therefore, if we want to do effective connectivity analysis on the neural level, not just on the empirical Bolt signal level, we have to pay attention what model we use, because unexplained variance will be accounted for as connectivity, neural connectivity. So we get wrong connectivity profiles if we use the wrong hemodynamic model. Now, why do I tell this in laminar fMRI course? So first, this is a local model, which means everything happens in the same voxel we are talking about. So the neurons are on this same level, the vasculature and so on. However, there's a known debate called brain versus vein already from '94. I want to illustrate in a few examples. This is blood flow. This is a posterior cortex, coronal view, this monkey, and they claim they can see orientation columns. This is from the 2002 from King and Duong paper. At the same time, they have also acquired Bolt signal, and what you see is the activation is highest in between actually the hemisphere, which is the sagittal sinus. So we have a venous signal, which is not at the end, not from the tissue itself, but neighboring from the tissue. So we have a venous problem already when we do standard resolution fMRI. And this will therefore become important when we go to high resolution fMRI. I want to show an example why this is actually also an important topic in standard resolution fMRI. This is a paper from 2015. They did sort of fearful faces and so on to activate amygdala. And what you see is amygdala activates here. This is the amygdala, they see activation. However, and it was visual stimulation, face stimulation, so you get visual activation. However, if you follow it with your eye at different slices, what you see is this red thing goes more and more closer to the visual cortex. So the claim of the study is actually there is no amygdala activation, or not primarily. What they see here as amygdala activation is actually just a draining vein from the visual cortex. So already in low resolution fMRI, we have the problem that we might get or we might assign activation to a certain brain area, even though it is not from that brain area, but from a vein which drains from a different brain area, especially if you have such strong activation as visual cortex, this might be a problem. There are also other studies, for example, from Brian Vandel, where he says we cannot study human V4 very easily because there's a vein going through. So, which means when people talk about V4, they might actually not see V4 activation, but some other activation. The second interesting study I want to show is from Bob Turner, where he sort of theoretically evaluated how big is the spread of this venous artifact based on the level of activation. So this is these different numbers are the area of activation, neuroactivation, and how far distant the spread is. And you see the higher the activate area, the bigger will be the spill over via veins. Now, why is this relevant for laminar? Again, if you have activation, for example, just in surface layers, you have to think about whether this comes actually from piled veins from a different area. So this is also something, again, we can learn a lot from standard resolution fMRI, especially from this kind of studies where when we interpret fMRI, grade neck fMRI, we have to be careful whether what we are measuring is actually what we want to measure. The final study I want to show is from Josine, who is sort of in the audience. This, I think, picture was already shown. This on top is grade echo, on the bottom is spin echo. Grade echo, you see nice activation in the cortex. In spin echo, even better. And you see the highest activation on the surface of the cortex. So this is, again, the effect which I was just describing. But I want to also point out something else. You see this yellow line. there's actually no activation in the tissue. This is just a draining vein from probably this part of the brain, which means you get, if you would do low resolution fMRI, you would get activation assigned to this part of the tissue, even though you see only the draining vein activated. And there have been recently papers from Sonja Kim's group using spin echo and grain echo and compared this. I highly recommend if you are interested in that topic. Anyway, this was sort of the long prelude to set the stage for the high resolution fMRI. First, the problem. This is a study from Leopold's group, no, Alexander Meyer's group. And here, what you see here is top is CSF, on the bottom is white matter. So one thing, again, also when you laminar fMRI, you have to get used to that white matter and CSF are always differently oriented depending on which study you're looking. Electrophysiology, CSF is always on top because they stick electrode from the top and then they go through tissue, which means therefore their spatial dimension is top to bottom. CSF is top, bottom is white matter, and then x-axis usually in electrophysiology is time. So just remember that this is the case. So I don't want to go into too much detail what this is showing, but what you're saying is sort of source and sinks, so neuroactivity, and you see a very complex profile with so time-dependent early sort of activation in the middle and bottom layers, and then later means 100 milliseconds, later than the surface layers. Again, this goes back to the question, what will we expect if we do fMRI? Again, I don't want to talk too much about this issue because neuroactivity itself, I don't think we have a very good grasp at this moment what's the neurocorrelate of the fMRI signal. Anyway, if you measure with grain echo fMRI laminar profiles, now white matter is on the left and CSF was on the right. In some other studies, you will see CSF on the left and white matter on the right, so get used to being confused. And again, everything makes sense. So CSF layer 1 is close to CSF. So therefore, if you count this sort of numerically, 1 has to be on the left and white matter has to be on the right. If you think from grain echo ball that we are measuring vein flows from the bottom to the top. So therefore, white matter has to be on the left and CSF on the right. So all of them make sense. Just when you then interpret data, just pay attention what the x-axis is. Anyway, this profile does not look anything at all compared to electrophysiology, which means if you do grain echo fMRI signal, the profile you're getting will not be what you would expect electrophysiology for feed-forward or feedback, which means there's something going on which either the fMRI is not a good representation of the electrophysiology, how it's measured, or there have been some transformation which makes actually this profile look like this profile here. And this one of these transformations I will show now in the next few slides. This has been shown, I think, by John in the first day. So this is the vasculature. Surface is here, CSF, white matter is on the bottom. The blood comes via the pial arteries, and then it goes through different layers, to the capillary bed, venules, and then it's picked up by the ascending veins to the surface where it's then taken out of the brain. Just terminology, I call the arteries diving arteries and the veins ascending veins because that's sort of what indicates the direction of where the veins are going. Now, if we take the first part of my talk and we would model each of the layers, we could model the same way as we do modeling the standard resolution fMRI. So for each layer, we have then a blood flow goes in, we have a change in the oxygenated hemoglobin indicating Q and volume indicating V. And for each layer, we would have a separate model at the end. So we have, if we have 6 layers, we have then 6 different independent model of the hemodynamic response. Now, the reason why in the standard resolution I point out the vein problem is we can, in the standard resolution fMRI, we can often ignore the vein problem because when we, for example, analyze connectivity, we average an ROI, then the vein which is draining is within the ROI most of the case, so we can ignore the spatial dimension. However, if we do laminar fMRI with gray echo, we cannot ignore the spatial dimensions. So, which means we have to take into account the deoxygenated hemoglobin changes from the vein, from the ascending veins. Which means if you look, for example, at this layer, we have flow going in from the arteries, we have change in deoxygenated hemoglobin and volume. This goes in the ascending vein. It's just not a compartment, but this ascending vein is fed by or is sensitive to the change of deoxygenated hemoglobin from the layers below. And then there's an outflow of deoxygenated hemoglobin, oxygenated hemoglobin to the layer above. So we have to have this spatial dependency taken into account in order to be able to describe theoretically what's going on here. So I will just show a few equations just to explain you what the concept behind this is. So the ascending vein compartment, if you have look at one layer, this is now the volume change. The change in volume is how much blood flow is going in, how much blood flow is sort of changing, how much blood flow is coming from the layer below, and how much blood flow is going up to the upper layer. So we are just at the end counting, and that's just mass balance. So mass balance is a physical principle that nothing sort of disappears, which means we have flow coming from the same layer, flow coming from the layer below, and flow going out to the upper layer. So we just count, it's just mass balance. We just count what goes in and what goes out. So if we don't have a blood-brain barrier leakage, that sort of this equation cannot be wrong because it's just mass balance. The same we do with deoxygenated hemoglobin. It looks a little bit more complicated, but it's not. It's just the concentration of deoxygenated hemoglobin multiplied by flow is the amount of deoxygenated hemoglobin going in, coming from the layer below and flowing out to the layer above. So that's, again, just counting how much goes in, how much goes out. And then that's described here, inflow from venules, inflow from lower layer, and outflow. Now we can just divide by the baseline parameters and get normalized quantities. So all the small letters are now normalized quantities. And then what we have are some ratios of the baseline parameters, which means if you have baseline parameters, baseline flow, baseline volume, and have the input function, we can calculate all the dynamics in all the layers. So as a feed-forward model, is relatively simple because you make just reasonable assumption how blood volume is distributed over different layers, how blood flow is distributed over different layers, and then you can, in a feed-forward way, calculate the profiles, what would result. And then here I want to show a few exampple. So on the left, this is blood flow. The spatial dimension is the y-axis, so white matter is on the bottom, CSF is on top, and x-axis time. And in this, we have assumed we have two peaks in the blood flow. We have one peak close to the surface and one peak in the bottom layers. And if we then use this equation, which I just described in the previous slide, what you are getting is the profile on the right. This is the gray-necker bolt signal. You will agree that these two peaks are not very well. Okay, these two peaks are not at all represented in the bolt signal. So it's very, very difficult to imagine that this increase from the bottom, from the white matter to CSF, this increase actually caused by these two peaks in the blood flow. And the blood flow is sort of a good reflection of neuroactivity. To first approximation, we assume that blood flow is a good representative of the laminar profile of the neuroactivity. Whether this is correct or not, this is another debate. But so so which means if we remind us back to the electrophysiology versus gray-necker bolt profile discrepancy, the model, just by assuming this ascending vein effect, actually says if you would get the same result, there's something wrong, which means the ascending vein already predicts that the neuroactivity and the gray-necker bolt should look very, very different. And that's sort of what we are getting. This is sort of now shown in a 2D version, white matter on the left, CSF on the right this time. And then you see the two peaks of CBF. in red. And the bold signal, you have sort of some hint of a peak here and here, but it's actually looks more or less linear increase. So it's very fascinating that actually this red is the input and the purple one is the output. Now, there's one interesting finding which I want to point out, which I myself did not appreciate too much, is if you look at the peak of the blood flow, it's sort of around, let's say, 70% of the depth. Whereas if you look at this, a little bit this faint peak of the gradient echo is at 90%. So we have a shift of the peak in the bold signal. So when people analyze, for example, just the bold signal directly and look at the peaks might be actually shifted compared to the input of the reactivity, even if you see them, which means that's an interesting thing. And actually, when I reviewed the literature in this paper, 2018, I looked in the animal literature. Actually, this is a very consistent finding when they measure blood flow and bold and blood volume and bold, that the bold peak was, even if they saw a very clear peak in the bold signal, was always shifted a little bit towards the surface. And this, I think, we don't appreciate too much at this moment, that there's an effect, not only the slope, but there's also a shifting effect. Okay, now how do we, if we know that the bold signal, just how it's measured, is not reflecting well the blood flow and the reactivity, is there a way to go from the bold signal back to the reactivity, so the model inversion? And there is a way, and David Norris group David Norris showed it on Monday, and here I show our approach, which is very similar. On the left is white matter, on the right is CSF. And this, what you are seeing is, because we have a model, we can just assume a certain laminar profile of neuroactivity and look what happens in the bold signal. So we assume blood flow changes only in layer 6, and then calculate what happens, how does layer profile in the bold signal look like. That's what you're seeing here. That's this light blue curve. If you have activation on layer 6, then we get obviously an activation in the bold signal in layer 6. But because of the draining vein effect, we get also some activation in layer 5, 4, 3, and so on. Then we can repeat the same thing. We have activation on layer 5. Because the flow is towards the surface, we don't get any activation in layer 6, but we have a draining vein effect towards the upper layers. Now, this information we can actually then use to calculate back from the empirical bold signal how the blood flow signal should look like, based on this knowledge of the leakage from one layer to the next. And which means we have, this can be quantified as this so-called peak to tail ratio. So how big is this leakage to the upper layers compared to the peak? If the blood volume of veins increases by a factor of 3, which means the veins in the bottom layer are 3 times has 3 times as lower volume compared to top layer, you would get this curve, peak to tail. Whereas if it's 6 times, you get this one. So it's actually relatively constant, which means you need this increase in blood volume from bottom to top in order to get certain effects. But within a wide range, actually, this leakage is relatively constant. So that's a sort of good news for people who want to do leakage correction, that the weights are actually relatively stable. This is very similar to what David Norris did. They did it in 2016, and they have published a very nice paper in 2020 where they generalized it for n layers, because this now for 6 layers, all the weights change if you're depending on the number of layers. If you have 10 layers, you cannot just interpolate, because this sort of cumulative effect, the 30% is all the effects. So you cannot just take the values in between, because then you would overcorrect it. So they have derived some formulas depending on number of layers. So if you in your study have 10 layers, you can go to this 2020 paper to drive the weights you need for your correction. Now, how do we use this knowledge? We say the true layer 6 activation is the measured activation. So S is the measured activation, and the LA is the layer activation, which sort of is the corrected one. So we say the bottom layer has no draining vein effect. That's obviously an assumption. so therefore the signal is correct. The layer on top of it, we take the measured signal and subtract the activation from the layer below with this weights derived from this model. So you can either take this model or this model, they're both very similar. And then if you go to layer 4 and we do the same subtraction. So what we are doing is at the end, we start from the bottom layer, go to the next layer and subtract the effect of the layer below. And then we go to next layer and subtract the effect on the layer below, and so on. We do sort of sequential subtraction and removing this draining vein effect. Now, I had some discussion on Monday. These weights are obviously not objective numbers because we don't know the true numbers. So they depend on the number of layers, but also they might depend on the brain area, because we know, for example, V1 is differently vascularized than other brain areas. So the vasculature is very different. So these weights cannot be the same. And then obviously it will depend also on voxel size and other parameters. So therefore, as a good practice, I will comment on this. We have to do some sensitivity analysis. Now, we have applied this approach in this 2018 paper. These are the measured profiles. Left is white matter, right is CSF. Top is V1 and bottom is V2. Actually, I'm not sure if this is correct, whether this V1 or this. Okay. Anyway, for this purpose of the talk, it doesn't matter. You see, especially here in the bottom one, you see this increase from bottom to top. What sort of is often seen. The different colors are just different conditions, different stimuli conditions. So you just have to pay attention to one. Now, if we apply this sequential subtraction approach, which we call deconvolution, but strictly speaking, it's not deconvolution, but let's call it deconvolution at this moment. If you do this deconvolution, what you're getting, again, look at this bottom, what you're getting is actually this nice peak in the sort of more or less middle layers. So this is very promising because we used a very, very simple stimulus. And for this very simple stimulus in monkeys, for example, with electrophysiology, when they did similar stimuli, they saw the strongest activation in the middle layers. And that's what we are getting after the spatial deconvolution. So that's very promising. Obviously, it's not a proof, but this is already, we know that the left is not correct when it comes to comparison with neural activity, and that the right one, this correction leads actually to something which looks very similar to what we expect from electrophysiology. Now, as a cautionary remark, because we don't know the weights really, what I would do is do the same thing as we have done, but then do a sensitivity analysis by varying the weights. So if we assumed leakage is 0.3 from one layer to the next, perhaps you vary your weights from 0.25 to 0.35 in order to see whether this peak remains if you vary the effect. So as good practice, I would recommend to do sensitivity analysis on the weights. My experience is actually this kind of effects do not go easily away. So within a range, it has to be obviously, the weights have to be larger than 0 and below 1, because it cannot be negative and it cannot be 100%. So we know the range is anyway around 0.2, 0.3, 0.4 maximally. So the range we already know, and within that range, this kind of effects will not go away. So therefore, if you do a sensitivity analysis, you will have good chances to convince reviewers that you're not too much model dependent. The second observation is, if you look at this curve, what feature of this curve leads to this peak? So this is actually very surprising because it looks like it's just an increase from the bottom to the top, like linear increase. Why, after doing this, we get a peak, a very pronounced peak? And the reason is, my explanation is like a second derivative. So if there would be a constant slope, just a slope, if you subtract the same weight, what you will get, it's just a straight line, or it might be decreasing or increasing, but you will not get a peak. But if the slope changes, then you will get a peak, which means non-linearities in your original curve after spatial deconvolution will give some features in the deconvoluted profiles. And so therefore, you have to pay attention when you look at the profiles, whether sort of there's some non-linearity. And then in the next slide, I come to different corrections, but this means if you would subtract, for example, the slope because there's an approach which says we should just subtract the slope. If you would subtract the slope, you would actually get a flat line. It means the subtraction of the slope will not give the same result as spatial deconvolution. Anyway, so this is a slide from Renzo, where he assembled the different approaches, how they deal with the macrovasculature effect. And I want to just comment on these effects a little bit. So one effect is the one I just mentioned. You have the macrovascular effect. Now white matter is on the right, CSF is on the left, so don't get confused. And you have an offset, which means a linear offset. The signal, this macrovascular offset, increased from bottom to top. And the true neural response, and hence the microvasculature response, has two peaks, like in the motor cortex. So if you add them up, you get this kind of profile, which means there are then approaches which then say we just should do detrending. And there are a few papers published on this. Now, if you would, as I said, if you would do detrending on this one, you would not get a peak. So therefore, this subtraction approach is very different from the leakage approach. The second thing is it's not physiologically clear what actually this macrovasculature offset means. If there's no, say, activation layer 6, 5, or 4, would we still add a macrovasculature offset in layer 6 and 5 and 4? So there's a very unclear what the physiological basis for this additive effect would be. So therefore, I don't think there's much arguments for this approach. The other one is a gain approach, where it says we have, again, this true profile, and then we multiply it by a certain function which also increases towards surface. This has the advantage if there is no activation in layer 6. If you multiply with 0, you still do not get any value, which means you don't create an artificial activation in a layer where there is no activation. This is an approach which we also proposed in 2018. However, we didn't say it takes care of leakage, but it takes care of sensitivity. So in low resolution fMRI, what is known already from mid-1990s, Banatini has done some studies on this, that the biggest activation you see in large veins. If you want to sort of normalize it and remove sort of the distraction of these large veins, you divide by either by hypercapnia or by standard deviation in order to make it more sensitive to tissue. This is sort of at the end a way to normalize the Bolt signal by taking into account the effect of the baseline blood volume. The more blood volume you have, the easier you get activation of the Bolt signal. And for example, in people who do auditory fMRI, they know that there's a vein going very close to the fMRI. If they want to see tonotopy very well, they usually exclude the strongest activations, because they say the strongest activations are veins and they are very unspecific. So let's remove the highest activated voxels in order to get it more sensitive. So this is again an implicit way of removing the blood volume effect. But this blood volume effect does not remove the leakage. I have some equations. I don't know how well you will be able to see it. I derived it yesterday, so I don't know, do I have time to go through it? Okay, I will just describe the concepts behind it. You don't have to understand every detail. So the fMRI model, what I've shown before, usually they have the structure as you have a function of baseline, like the baseline blood volume, baseline oxygen extraction fraction, and you have another function which is dependent on activation. So this is like the Davis model from 98, but also the balloon model from 98. They have this kind of structure. So the Davis model is written here. The signal S is a scaling constant times some physiological parameters. And this scaling constant is a function of blood volume and so on, also field strength. Now, one way of taking this A out, the scaling constant, because we want to be only sensitive to the physiological effects. So we want to remove all these effects which are based on echo time, T2 star, and so on. So what people do, for example, hypercapnia, they say we measure actually this A constant, this scaling constant. So if we have two voxels, in two voxels we have the same neuroactivity, but the bold signal is here 2%, the bold here is 1%. So it's not reflecting the level of neuroactivity, but it reflects how sensitive we are. For example, if you have a surface coil and so on. So we are more sensitive to some voxels than other voxels. And then if you have a condition like hypercapnia, you can actually determine the scaling constant and remove it so that you are equally sensitive towards all voxels. That's at the end what this equation says. So in low resolution, we just divide then the normalized stimulation response by the hypercapnia, and then this A, which is voxel specific, just cancels out, and then what we are getting is just physiological parameters. Now, if we apply the same approach for laminar fMRI, we say, okay, we have just for 2 layers, we have one layer, we have sensitivity of that layer plus multiplied with the activation of that layer. The layer above, we have another sensitivity, we have the activation of that layer, and we have the draining vein effect. That's this term. So we have to add the draining vein from the bottom layer. So that's this equation, what this equation means. So just the leakage model. If we now write the same thing for hypercapnia, we get another equation, and we assume certain things are constant because there is no activation. So we get another equation. If we now divide the stimulation with the hypercapnia, we don't get rid of the leakage. That's at the end what we are saying, which means what works in low resolution standard fMRI, normalizing the bold signal across the brain by doing calibrate bold or other approaches to remove the sensitivity of the voxels, which are different for each voxel, doesn't work for laminar because of the leakage effect, which means because people are starting to do calibrate bold in laminar, you cannot apply the same calibrate bold approach to get to oxygen metabolism by using hypercapnia, but you have to do leakage correction. However, what we still do is, coming back to this picture from Renzo, is going back to this one, we still remove the sensitivity for different layers. So if you have different blood volumes, we remove that effect. So we have sort of 2 effects which are confounding our results. One is the sensitivity to each layer, and the other one is the leakage. One of the effects we take into account by division approach, the other effect we're not taking into account. Okay, that's at the end my it's a complicated story, but you will see the slides and you can work yourself through the equations, and hopefully things become more clear. Now, therefore, from this consideration, the division approach, which we propose and other people have proposed, also doesn't work, which means if you have 2 conditions, dividing one condition by the other condition will not give you the true profile. So subtraction does not work, and division does not work. And there are papers, laminar papers, who are using one or the other approach. So therefore, the only way for the gradient echo fMRI to correct is this leakage correction approach, which we have proposed, but also there are, as I said, David Norris paper, there are older papers from Jakob Heinzle, Klaas and Stefan, and so on. So therefore, we are not getting around to correct for leakage approach, leakage factors when we do gradient echo bold. Okay, then I switch now a little bit the topic. This equation, this model, we can now investigate to look for explanations for common observations. One of the observations you have heard on day 1, I think it was Josine or David Norris who talked about it, the so-called bump. The correct word would be intracortical local maximum, but it's a little bit too large, so bump is a little bit better, which means what people have seen when they look at layer profiles, already the uncorrected one, they saw an increase, local maximum in the middle. And there has been debate whether this local maximum is vascular or it's neuronal. The reason why the vascular argument is put forward is, for example, in V1 and V2, the layer 4 has higher blood volume. And as I previously argued, the blood volume is a factor which describes the sensitivity. So if you have higher blood volume in layer 4, perhaps this bump, what people are seeing, is due to higher vascularity. Now, the good thing about this forward models is you can put in the numbers and then look whether one or the other explanation is true. So in the paper, what we have done is we have described 3 different hypotheses. It's a little bit small. This one is the neural hypothesis, which means the cause of this bump is, there's a bump in the neural activity, which means layer 4 is, or middle layers are highly activated on the neural level, but the vasculature is flat, which means baseline blood volume in red is flat across all layers to isolate whether the neural activity is causing the bump. Then we have the vascular hypothesis, means we have a high level of blood volume in red in the middle layers, but the neural activity in blue is constant. And we have the mixed hypothesis which also makes sense, if you have higher blood volume, there's a reason why there's a higher blood volume, because neurons are usually on average more active. So the mixed hypothesis says, yes, there's a higher blood volume, but there's also higher neural activity for simple stimuli like a checkerboard and so on. Now we put in all these scenarios into the equations, and what we are getting is shown here on the right. Left is white matter, right is CSF, and the different colors are different hypotheses. So the green one is the vascular hypothesis, the purple one is the neural hypothesis, and the mixed hypothesis, which is probably the most realistic one, is the red one in dotted. And what you see is the vascular hypothesis actually doesn't give any peak, which to us was very surprising. Only when there's neuronal activation, which has a bump itself, causes a bump in the Bolt signal. And there are 2 reasons for this. One is the smearing effect of leakage. So even if you have vasculature higher in one layer, it smears it's blurring towards the surface layers, which means the peak a little bit disappears. The second thing is, if you take vascular hypothesis seriously and say neural activity is the same, actually the relative neural activity has a dip, because you divide by a large number, the change in oxygenation or blood volume is, you have to divide by a large number of blood volume. Actually, the oxygenation change is smaller. So the true vascular hypothesis is actually a little bit more difficult to understand and to do correctly. And I had a conversation with John on that in Montreal. So which means in the literature, there are 2 hypotheses, especially in the animal literature, that when they observe a bump in the middle layers, on the empirical measured laminar profile, that it's vascular or neuronal. This model helps us to say, if you see a bump in the middle layers on the original data, it has to be neuronal, which means that's good news for you. Even if you don't want to do leakage correction, if you see a bump in one of the layers, after leakage correction, it will still remain there. It will actually be more pronounced. But even without leakage correction, you can be sure that the neural activity in these layers was higher. So that's good news. Even without modeling, you can make some cognitive neuroscience statements. The next thing, the model itself is dynamic. So I've shown so far only steady state responses, but we can calculate different time courses. So we want to know what's the delay if all layers are active at the same time. So there's no delay on the neural level. Is the Bolt signal at all layers also simultaneous or not? And what we are finding is, so this is the setup, what we are finding is this is the Bolt signal change, and different colors are different depths. So x-axis now time, and superficial layers are more red, and the deep layers are more in blue. So one here on the zoomed version, I don't know how big this is for you, but you see the blue one peaks earlier, around say 3.2, whereas the top one peaks around 3.8, 3.9. So we have a 0.6, 0.7 second delay between the bottom and top layers, just pure to vasculature. So the neural activity was all at the same time, and the hemodynamic response of the microvasculature was also at the same time, but the vein effect smears also not only spatially, but also temporally shifts the peak. Now, this will have consequences when you do connectivity analysis. For example, if you do Granger causality, which relies on temporal relationship between different layers and different brain areas. If one layer is 0.5 seconds earlier than another layer, this might be already due to vasculature. So that's something, again, such kind of models can sort of point us to certain explanation of observations. And here I have shown, I show some observations from 2002 from Alphonse Silva and Koretsky, then Hirano and Tian. Also in this model, we had the initial dip. We actually see very similar observations, what they observe, and it looks like it is the vasculature and the ascending vein effect already explain some of the delays, what's observed experimentally. Okay, now to the last part of my talk, how I'm with time. Okay, 15 minutes. Okay, I will be a little bit faster. Now, this second part, what I've shown is just the vasculature ascending vein effect. But if you want to model the entire chain, we have to model from the neural level, the vascular level, and the voxel level. The voxels are also limited resolution because in the previous considerations, we didn't have any voxels. Now, the first paper we have published, the laminar model, is actually just describing the vascular level. So in the other paper in 2021, we added sort of the voxel level, including angular dependence, orientation dependence of the Bolt signal, and we have added the neural model to the model itself. So at the end, what you see is the standard model from here to here, and then we have the laminar model from here. So it's a combination of the standard low resolution model with the ascending vein model, laminar model, and then at the end at voxel blurring. Now, in this study, we also investigate a few more things. In the other one, we just look at single conditions. In this study, we looked a lot on condition differences, because sometimes people argue if you have a single condition, it might be misleading, but if you have two conditions which have the same bias, perhaps the subtraction of these two conditions will give you something nice. And I have argued in earlier slides that actually this is probably not correct, except in cases where you have the difference between these two conditions are localized in certain layers. Then actual differences might be quite good. So this is shown here. We have sort of one condition in blue, and then we have another condition dotted, and large dashes and small dashes, two different conditions. And then this is sort of in the activation bottom layer. And if you then calculate the Bolt signal, the blue one, as argued, is very deceptive. But if you look at the difference between the blue one and the large dashed red one, actually the biggest difference is approximately at the layer where we are seeing it, which means if you find tasks where the two conditions are very similar in the activation profiles, for example, they activate in the same way in a feed-forward way, but then you have attention modulation. So you add only activation in one layer without changing the activation in other layers, condition difference might not be a bad way to go. So this is sort of one interesting result from here, but this is sort of a art of experimental design to find good conditions which are very similar to each other. The other thing is we have looked at angular dependence, which means the Bolt signal, as John and other people have shown, the sensitivity is depending on the orientation of the vessels. So, and which means if you have gyrus and sulcus and walls, then the same neuroactivity will give you a different Bolt signal depending on the orientation of the blood vessels or the cortex relative to the field strength. So this is an, I think, important effect which has not been taken into account in the analysis so far. So you see, for example, if we add the angular dependence, we get the very strong activation in the sulcus. This can obviously not be generalized because in some part of the cortex, it might be the gyrus, which is more activated. And then if you voxelize it, then again, it looks a little bit different. Then we have looked at different conditions. Because of time constraint, I will not go into that. What I want to say is, you see here some distribution of these dots are sort of different voxels. Now we assume no noise. So this distribution, this variation of the bold signal just comes from the angular dependence that we have a limited spatial resolution and the voxels are certain orientation relative to the field strength, which means sometimes we might actually be better in terms of signal to noise, but this angular dependence might look like noise, and perhaps we should correct for this in the future to actually get better signal. I skipped this one. One important message what I want to get across is, because I see paper or this discussion, how many layers should we assume when we analyze? So some people say we should have 20 layers. Some people, a lot of studies do 3 layers, because they say, I'm just interested top layers, middle layers, or bottom layers, because they are describing the processing streams. So whether there's feedback or feed forward and so on. So I'm only interested in 3 distinctions. Why should I determine more than 3 layers? And the argument is, mathematically, you need more layers than your distinctions. And this is sort of shown here. Perhaps in this I probably can do since. So we have this sort of the ground truth. Again, it looks very noisy. And all of the noise comes actually from the angular dependence. And we said from this one, original data, we calculate now 3 layers. Now, the biggest activation difference we induce in the bottom layers. However, what you see, and if you have 3 layers, the biggest difference is actually in the middle layers, which means if you have only 3 layers, the biggest difference, what you might get, might be in the wrong layer. So this, we sort of intentionally induced the biggest difference in the bottom layers. However, if you would do analysis of just determine 3 layers, the conclusion of your study might be these 2 stimuli differ in feed forward because the biggest difference is in the middle. So therefore, you have to be very careful when you analyze laminar data, because the more you determine, the more layers you determine, the narrower is the point spread function. Obviously, you're limited by the number of voxels and your signal to noise. So I think a good compromise would be something like 8 or 10 layers. We actually show theoretically that 8 layers already is quite good, and more layers will not improve much. So therefore, even if you are interested in only 3 distinctions, top, middle, and bottom, you have to start with more than 3 layers. You can later pool together the layers. So you can say layers 1 to 3 are my top my feed forward or feedback, and layer 4 to 6 are my feed forward. You can later group them together, but in the analysis, what you have to do is first determine from the layer fMRI signal more than 3 layers. I think that's a very important thing, and I think this should go sort of in the consensus. We need more than 3 layers, even if we are interested only in 3 neural distinctions. And this is sort of showing the same thing, a little bit more complex, but this is even after. This is it's too complex, but this is after model inversion neuroactivity. So if you look at the blue curve, the original one was flat, more or less flat, whereas in the blue curve it shows maximum in the middle layers. So this is sort of quite bad. However, again, in this one, if you look at the condition differences, actually condition difference again better. So therefore, as a good practice, it might be good also to not investigate 1 condition alone, but 2 related conditions, which might reduce some of the bias. There's no guarantee that your bias will be gone, but at least you have a little bit more control over the difference you are seeing. The final result I want to show is, this is inspired by Emily Finn. We just tried to model what they were observing. They had sort of 2 conditions. One, they observed or they claimed there's an activation in top layers and bottom layers. And then in the other one, there's a delayed response in the bottom layers. If we feed it into the laminar bold model, you see actually activation in top layers, but the bottom layer activation is almost not visible. Again, this is this increase towards the surface. However, if we have the activation most in the bottom layers, also there we almost don't see the bottom layer activation. So the bold signal is really very, if you take it at face value, the great angle bold signal can be really deceptive. And this is then when you show it in voxel, you would buy this, it's very small, but later you can go over the slides. If you look at the voxel distribution, you would not actually think the main cause of this voxel distribution comes from the bottom layers. So it's very deceptive if you take this that as pure reflection of neuroactivity. We did a dynamical model inversion on this kind of data, and what we are getting is a little bit pixelated, but we're getting sort of the profiles back from the original response. The last thing I want to show is sort of an effect which is not taken into account in this modeling, is the so-called blooming effect. So blooming effect is saying if you have a vein, I already described the physiologically the spatially distinct effect. So it means you have activation here, but the vein, the oxyhemoglobin changes here. But we have another remote effect. If you have a vein and the deoxyhemoglobin changes in that vein, also in a voxel which is further away, you will see fMRI signal changes. And the reason is the magnetic susceptibility disturbances of the blood vessel does not stop at your voxel border. It goes to the next voxels, which means even in voxels where you don't have any change, the vein can affect the fMRI signal in neighboring voxels. And this is sort of shown in the Jeff Dunn study, but this actually was already sort of at the birth of the fMRI in 1992 by Ogawa, where he let sort of rats inspire different level of oxygen and the veins gotten darker. Now, that's already well known, but if you look at, for example, at this vein, ascending vein, it is quite a sharp line. But if they have then injected a different amount of iron, when you go here, this line looks much broader. And then actually there's also a dipole effect, so you have an increase in signal. So you have a complex effect, which means the vein, if you inject the contrast agent, that's already known in the clinic. If you inject gadolinium, blood vessels look larger after injection of gadolinium. And this is the blooming effect, which says blood vessel can have effects not only in the voxel where the blood vessel is located, but also in neighboring voxels. And this is, there have been many studies already on this. This is from Karl Scheffler's group, this figure, but there's also from Michel Morel, and there are other studies where they looked at how large is the activation as a function of distance from the vein. And what they have shown is, I will not go too much into depth of this figure because of time, but what they are showing is the bolt signal, the further you are from the vein, the smaller the bolt signal comes. Obviously, you can also argue that it might be a physiological effect, because if there's a large vein, there's also ascending vein, which means there might be also a true physiological effect, but we already know there's a physical effect due to the blooming effect. There are methods who want to correct for this. Ravi Menon already published in 2002, and he has a recent paper 2021, where he suggests using the phase image to regress out this large vessel effect. However, as a ironical thing, perhaps this ascending vein effect, which is just purely physiological, this sequential subtraction might also subtract some of the large vessel effect. But there is no guarantee for that. But this is something would be an interesting thing to test. Okay, and the last minute, future work. You have seen the entire model looks like this. However, we know that this neural model, the excitation inhibition are not independent for each layer. And where we want to go is a model which is sort of a microcircuit model. Top would be CSF, bottom would be white matter. We have a complex circuitry. We want to substitute this simple excitation inhibition model with the complex circuitry. And with that, just a summary. Take-home messages: the gradient echo bolt signal, we have a problem with the ascending veins. This leads to a blurring towards the surface of the brain, and this leads to a very distinct profile compared to electrophysiology. Spatial deconvolution is a simple method which might remove the part or fully the ascending vein effect, and also may reduce the blooming effect. Condition differences are better than single conditions, but not any condition difference. The condition difference have to be sort of presumably be matched in the layer profiles, except the layer of hypothesis layer of where the difference occurs. determine more layers than you need. So if you need only 3 neuronal layers, you have to, on the bold profile, determine 8 or more. Dynamic model inversion has not been applied so much, but I think there's a lot of potential to recover neuroactivity time courses. And then we have not removed the angular dependence of the bold signal, but I think this will remove a lot of the noise. Finally, I would like to do self-advertising my last neuroimage paper, because there will be no neuroimage papers anymore. But the last one I published is a summary and primer into all the different modelings, and the code of the standard resolution DCM hemodynamic model and the laminar hemodynamic model. They are in our GitHub and they are freely available. You can download and play around with that. And thank you for your attention.